Hello and welcome back. We are continuing our reverse engineering and power-up of an auction-bought Soviet space clock. It's from a Soyuz spacecraft and was authenticated as having been flown in space. In the first episode, we opened it up and we were greeted by a surprisingly complicated and beautiful electronic assembly. In the second episode, Master Ken was able to reverse engineer most of it. He explained what each board and each component does, in particular the details of the power supply. We think we now understand it pretty well and have a plan to power it up safely. Of course, we would never just apply power and hope for the best. The last thing we want to do is risk destroying some of the precious circuitry. So the first step is to remove some modifications, which we think was from a previous failed attempt to power up the clock.
So you can see there have been some wires added for external powering.
Mm-hmm.
So these two wires were added to the 5-volt output for the chip. These two wires are wired right across the power transistor, which doesn't make any sense.
I'm going to try to remove the old wires. Okay, so that was badly soldered. These were just add-ons, so that's not a problem, but the original wires, they are so well soldered. I don't want to. I'm hesitating to remove them for testing. Never be able to do it as nice a soldering as they did. Okay, so those bad wires gone, and there's two more on the back. Okay, got that one. This is a power transistor. There you go. Got it. Okay, so we're back in the original configuration. I would say let's try it. I mean, the capacitors, they are so well put in there. So Ken and I were debating whether we need to check the caps, and to do that we somehow have to take them out of circuit. But they are so well put in there. There is some epoxy at the lead, or some very hard stuff, and there is a tie on top of them. So this has been done to the nth level to assure that it would resist vibration. So can't remove that without damaging the board. I said try them in circuit and see what happens.
Yeah, I guess so.
So we need the pins to poke through the conformal coating. That seemed to work. 9.9 microfarad. Yeah, it says 10. 1.99 microfarad. And this one says...
I think it says 5.
No, it says 1 point something. 1.5.
1.5.
I would say this is good Russian capacitors, and they're all good. 2. And this one is also 2. 2 microfarad. They come all exactly at 2.00. $64. Can be right. This one is in parallel with something. So which one were we measuring?
This is the one.
Okay, that's the one that reads weird.
So it goes here, here, here. It's connected to everything.
1.6, 25 micro, 250 microfarad. It says 170 on it.
Seems like you get more microfarads than you pay for.
And this one is 192. And same thing, it says, I don't know what it says, 170. It's very close and on the high side. And also I'm testing them at 1 kilohertz, so at 100 it might be lower. I would say the caps look good enough. Alright, the electrolytics check out good, as expected. We are go to try the power supply. But before we do that, we want to disconnect it from the rest of the clock so we don't accidentally fry the circuits in case the power supply malfunctions. After much debate, we decided to carefully desolder the power wires at the posts. I was able to do it by sucking out the solder with the desoldering pump and slide the wires off without altering the carefully trimmed original looping of the wire. I can desolder it and preserve the beautiful loop here. So we managed to take the wires out and preserving the loop, so I can resolder them exactly the same way. And the thinking is to power it up and make sure that we don't have any over voltage or something like that, right? So we're sort of ready to power, actually to test the power supply of the clock. It's going to go on the load. This is my HP 6060B electronic load that I restored in a previous episode. A very handy instrument that allows you to load a power supply with a constant amount of current, voltage or resistance in order to check the power supply under operation. And I've made a little connector back there, and I've been able to find one of those connectors. It's actually was cheap, but that's not the military grade ones, that's plastics, it's an imitation. So once again, super careful, we are powering the power supply is disconnected from the boards. We are looking at what it does on the electronic load and on the scope. Okay, so I think I have it all in one screen. 24, also it says 12, it's 12 times 2 because I have the 2 in series, I have a little series on. So 24 volts into the clock, goes back into the load, goes into the voltmeter, so I should have 250 milliamp, and that should come at 5 volts. And then we have the output over here. Alright, nothing goes. And it's 5.15. 200, and this is not very well calibrated, it should be 250. This is doing fine. I was drawing 120 milliamp for 250 out, so not that efficient. 50% efficiency, but it's low current.
What to measure the peak to peak?
1.8 volts, that's a huge amount of spiking. Alright, let me get the current up. Half an amp.
Okay.
Current 0.5, enter.
Might give us more action on the scope.
So this one up is still a little high. It did its half amp. Okay, 1 amp.
Sure.
So we think this can do at least 2 amps, can power 10 watts. So it's, oh, now it's getting close to 5 volts. So it's okay in regulating, and it's more efficient. So 350 milliamps in for 1 amp out. No heat whatsoever. Can't feel anything. So we call it good?
I think so.
I don't want to test it to more than an amp. We don't know what the maximum is, really.
Well, you know, multiplying out the number of chips, I estimated probably about 10 watts.
That much, huh? I'll be happy with my 5 watts test here. At least it won't burn the chips, which is what we wanted to check. Okay. Alright, power down. And I'll resolder the wires, and we're good to try again with the clock. Last one. Okay. Ready for power up. We have our power. I'm just monitoring the output of the power supply, but that should be good. It's just if something collapses, I know right away. And I turn the clock off, so nothing should happen. Are we good for lift off? Nothing should happen, right? Yeah, okay, so 24 volts.
No amps.
No amps. Clock is down. And 3, 2, 1, on.
Look at that. It's counting.
4.7 volts.
4.7, that's a lot.
Look at your volts here.
Oh yeah, something is, okay, hold on a second.
It's something to do with current limiting.
Yeah, so I was currently emitting too low.
But it was counting seconds very nicely.
Okay, so let me current limit. I set it fairly conservatively over here. I say a half an amp. Let's try 0.7 first.
Just if you see this volt dip below 12,
Right.
turn it off and go.
And then turn it on. And then
You dipped. No, you're okay.
okay, I'm good.
5.1 volts. Yeah.
Okay, that's better. So how's the clock doing?
Count it.
Alright. Well, it's Moscow time. So how do you set it up, Master?
So I think if we switch this, then this button should.
Don't you need to enter?
Okay, I have no idea how to.
You would think this would be.
Well, this is. I was trying to set it that we can go to stopwatch.
Okay.
So it's counting the seconds. Let's start. Then this will be stop, and this will be reset.
So we just have to find a way to
Set the clock.
set the clock and then set the relay. Okay, I put it all back together and I think we figured out how to do it. You press this thing, well, first you go into this mode, you press it, 1, then 1, 2, 3, 4, 5, 6, and then it's 30.
Yeah. 31 now.
1, 2, 3. 1 and then go. Whew. That's doing good. I hear a relay relaying. I hear something. And then how do I set the alarm? I go do the same thing over here and I do at 16:35.
And
Let's
then
try now.
You have to switch the correction one.
And then we have to hook up the relay contact. Okay. And now I should be. And then in 3 minutes, my egg should be cooked.
This should be a tedious video.
Well, I think the clock's working. So now we have to. You say you can control. You can control the set time from the outside.
No, the start-stop reset of the stopwatch.
That's it. You cannot set the clock.
Correct.
It's
Well-
just inputs. 3 inputs.
3 inputs and then 1 output for the alarm relay. So
despite all of its apparent complexity, the clock cannot be set from the spaceship, nor can it even give the time to the rest of the spaceship. There are only inputs to start, stop, and reset the chronometer from the ship, and one relay contact output that closes at event time. Finally, there is an extra input for an external frequency reference, which we think has actually been disabled on this clock. And that's basically it. Hey guys, we have a working Russian clock. Yeah.
And then the comma digit at the end here, I think that indicates something, but I'm not sure what. I couldn't figure out what it was connected to.
Carl, we have put the clock at 35. So
45 seconds, it should do something.
we should hear a click.
And
Okay, now 8. Yes!
Heard it.
Heard it. The relay clicked.
That was less dramatic than you might.
There you go, Russian clock.
Huh.
This is
So you didn't have to replace any ICs or anything?
this is
Reset the
wrong.
stopwatch.
This is wrong. We should be on Moscow time.
Yeah.
Yeah.
What's Moscow time?
Reset the stopwatch too.
So it's currently
One more.
3:36 a.m. in Moscow.
Okay, it's 3:36 a.m.
Wait, let me just verify that.
Then I do
Right. Correction mode.
correction.
Well, do Krasnoyarsk.
Yeah, 3:36
One.
a.m.
2, 3.
This is super error.
1, 2, 3. I'm becoming better at it.
Oh, because you have
One,
to delay and
two.
hold.
And if you
3,
mess up, you have to
4,
start all over.
5, 6.
Yeah.
Okay. Ta-da! Moscow time.
Cool.